Hello and welcome to this BME 306 tutorial. My name is Barrett. Today we're going to be talking about how to implement a system of ordinary differential equations in Matlab using Matlab's inbuilt ODE 45 solver. First thing we're going to do is open up a copy of Matlab and start a new script. For purposes of today, we'll be modeling out the system shown here. This is a 3-compartment model comprising a stomach, plasma, and kidney compartment, wherein we start with some drug amount in the stomach, which moves in one way towards the plasma, which then has a two-way interaction with the kidneys, which then eventually eliminate the drug through some wasting process. To get started, we'll first define the initial conditions for our setup before talking about how to model the code or how to run the code, how to plot it, as well as how to set up your model function. So starting with initial conditions, first thing we're going to want to do is ascribe some values to our rate constants. So for today, I'm just going to pick some arbitrary values for K1, K2, and K3, where these, again, relate to your rate constants. The next thing I'm going to do is set up the initial amounts for our compartments. So we'll say the stomach at time 0 is going to have some amount of drug 10 in it. The plasma at time 0 will have some amount 0, and the kidney will also have no drug in it at the start. So it goes without saying, but these are not physiologically relevant. Really just for illustrative purposes. One last condition that we'll need within our initials is our time span. So I'm going to define this as a vector from 0 to 30. This is just what time interval we're solving over. This can be seconds, minutes, hours, days, all depending on your rate constants and your initial amounts. Which, speaking of, I'm also right now going to pass those in to an array for rates, K1, K2, K3, and I'm also going to set up an array for our initial amounts, and that's going to be S0, P0, and K0. Great. And the reason I'm setting them up like that is because when we go to define our model function in MATLAB, the syntax looks something like this. Function dcdt or dadt is equal to model amounts and rates. You pass in all of your amounts of drug in an array, and you pass in all of your rates in an array. Because those are a bit tedious to deal with, though, I'm just going to really quickly break those back out into individual variables. K1, K2, K3 is equal to rates 1, rates 2, rates 3. And the amount in the stomach, plasma, and kidney, stomach, plasma, kidney, is going to similarly be equal to A1, A2, and A3. Once we have that set up, we can start writing out our differential equations. So, for instance, a change in amount of drug within the stomach with time, we'll call that ds dt. That's going to be equal to minus K1 times the concentration in the stomach. We can then say that the concentration in the plasma and how that changes with time is going to be equal to that same equation from before, but now positive, as well as K2, negative K2 times plasma amount minus K2 times the amount in the kidneys. And then finally, dk dt, we're going to set that to positive of this equation from the plasma, minus K3 times the amount in the kidneys. One last thing before we can call this system good is we're going to pass all of these variables, ds dt, dB dt, and dk dt, into an array dA dt. Just so that our function can make sense of it. Right now I'm going to save this just as BME 306. And we can move on to invoking this model through our ODE 45 command. So ODE 45 exports a time vector, column-wise, as well as a matrix of amounts, where each individual column corresponds to a species in our model, so that'd be stomach, plasma, and kidney, and each row corresponds to a time point. So we'll say t comma a is equal to ODE 45 at t comma a. We'll call our model, pass in some constant or some amount a, as well as our rates, and then define our initial conditions, so our time span and our init amounts as we defined up here. So that looks pretty good. We'll run this. And we didn't plot anything, but we'll see that in our workspace, all of a sudden we have a matrix called A that has corresponding amounts in each one of our 3 compartments for all of our time steps. To plot this, we're just going to say in our plotting compartment, we'll say plot t comma a, and we'll also define a legend that has our stomach, compartment, plasma, and our kidney. Just going to quickly label our axes as well. On the X, we'll have time, and on the Y, we'll have amount. So running this, we see a plot that pops up that has all of our amounts over time. And just like we'd expect, the stomach starts high at our initial condition of 10. The plasma and the kidney are down at 0. And really quickly, the stomach's amount drops off, where it moves into the plasma, which then slowly transports it into the kidneys. And if we were to run this for, instead of 30, if we were to up that to, say, 100, we'd get a similar plot, but now one that eventually tends towards 0 across all compartments with the elimination. If you want to beautify this plot, you can also say get 0 factory, get rid of the gray background, just as you're looking at making professional looking figures, but this would be up to the individual person. So run this one last time, and now we see we have the white background with our labeled X and Y axis, as well as our legend. So this is it for ODE 45 in Matlab. Thank you for listening, and best of luck with your projects.